Advert for a solar fan hat says the following. The solar cell can convert solar energy directly into electrical power, which can turn on a fan. Its fanning speed can change automatically depending on the availability of sunlight. Availability is a bit of a vague word, but we'll talk about that in a minute. The emission of electrons at the metal cathode of the solar cell is an application of the photoelectric effect. This availability of sunlight. Sunlight is white light and it's got some ultraviolet light, so its frequency does not change. Availability of sunlight is going to change the brightness of the sunlight, in other words, the intensity. So that's your number of electrons. Number of electrons directly relates to the current that is going to be generated. So let's see. Explain why the fan turns faster when sunlight intensity increases. So, explain why the fan turns faster. The bullets are: the greater the intensity increases the number of electrons. More electrons, more current, faster turning. Define threshold frequency. It is the frequency of light that will release photoelectrons. Calculate the threshold frequency for this metal cathode. So, the first thing is you are given the work function. So, work function is going to first need to be converted, 2,13 electron volts times by 1,6 times 10 to the negative 19, which turns out to be 3,41 times 10 to the negative 19 joules. The work function is equal to Planck's constant multiplied by the threshold frequency, so therefore the threshold frequency is going to be the work function, 3,41 times 10 to the negative 19, divided by Planck's constant, which is 6,6 times 10 to the negative 34. And that gives you 5,16 times 10 to the 14. Don't forget your unit hertz. Nikki shines green light from a 60-watt bulb onto the solar cell. The maximum speed of the photoelectrons emitted is given. Calculate the energy of a photon of green light. In other words, the total energy. What is total energy equal to? Well, the total energy is equal to the work function plus the kinetic energy. We've got the work function, so let's plug it in, 3,41 times 10 to the negative 19. Can we perhaps work out the kinetic energy? So let's do that. EK is equal to a half mv squared. I'm given the half. The mass of a electron is on the information sheet, and therefore we are able to actually substitute it in. It is 9,1 times 10 to the negative 31. How fast are these electrons moving? 2,39 times 10 to the power of 5, and that needs to then be raised to the power of 2 because it's squared. When I plug all of that in, I get 2,6 times 10 to the negative 20. I then have to add that over here plus EK. So over here I can add those two numbers together, and I land up with the total energy being equal to 3,67 times 10 to the negative 19 joules. Nikki replaces that 60-watt green bulb with an ultraviolet light bulb and holds it the same distance from the solar hat. Will this affect the maximum speed of the emitted electrons? Speed of electrons is got to do with the amount of kinetic energy that they have. Ultraviolet has got more, so a higher frequency. So this is equal to HF, and a higher frequency, the work function will remain unchanged, and therefore this speed would have to increase. During an experiment to determine the work function of a certain metal, light of different frequencies is shone, and the corresponding kinetic energies are given. Define the term work function. So, the work function is the minimum energy required to release photoelectrons, slightly different from the threshold frequency, which is the minimum frequency too. Use the data in the table to draw a graph of y versus x. You need to say graph of whatever y is versus x. You then need to put the first thing onto the y-axis, kinetic energy, and you should actually write out the word kinetic energy. Sorry, mine chopped over there. And it's times 10 to the negative 19 joules. That's also chopped a little bit over there. Let's maybe put that in. Anyway, and then you've got frequency, which is 1 times 10 to the power of 14 hertz. It was very kind of them to put those up into those headings for you to make it a little bit easier. You then have to evenly scale the axis. You must put 0 in and evenly scale the axis again. Plot your points and put a straight line through those points. What is the frequency of the point of intersection? And most of you got a fairly nice 5,5 ballpark, okay? Because, I mean, it could have been something a bit different, fractionally. And don't forget a unit, because it is in hertz. And then what is the term used to describe this frequency? This would be your threshold frequency. And then it asks you, use the graph to work out the work function. Well, you know work function is equal to h times the threshold frequency. You've got the threshold frequency. You know what h is. It's 6,6 times 10 to the negative 34. And you then land up times threshold frequency with 3,63 times 10 to the negative 19. Again, don't forget your unit, joules. We've got solar panels, and they contain multiple photovoltaic cells. They're used to convert the sun's energy into electrical energy. Use the diagram to provide a simple explanation of how the photovoltaic cell used. You don't have to explain this concept of a junction. So the first thing that happens is the energy from the photons from the sun dislodge the electrons or remove the electrons from the material. Those electrons then go into the silicon, and because they are free to move, they conduct electricity. So I'm going to write that down. You can see there's electron flow over there. So where did your marks come from? You needed energy from photons that then, oh, sorry, I haven't written there, dislodge electrons. I've left that out, dislodge electrons. So that's your second mark over there, and then they can conduct electricity. Gallium arsenide is a material that is commonly used in the manufacture of solar panels and has a work function given. Calculate the threshold frequency of this material. Well, the first thing I need to do is I need to change this 3,2 electron volts into joules. So it's 1,6 times 10 to the negative 19. And that is going to be the work function of 5,12 times 10 to the negative 19. Threshold frequency is equal to work function divided by h, and therefore I put 5,12 times 10 to the negative 19 divided by 6,6 times 10 to the negative 34, and that becomes 7,76 times 10 to the 14 hertz. Consider the wavelengths of visible light and your answer in 3.2 above. Show by calculation which component of sunlight is essential for the solar panel to produce electrical energy. Many of you wasted a great deal of time on this. The first thing to do is to say, I've got the threshold frequency, let me work out the wavelength. My threshold wavelength is going to be the speed of light divided by the threshold frequency, which is 3 times 10 to the power of 8, divided by 7,76 times 10 to the negative 14, which I've just calculated. I then get 3,86 times 10 to the negative 7 meters. But over here, I'm working in nanometers. So let me convert that. It becomes 386 times 10 to the negative 9 meters, which is therefore equal to 386 nanometers. Where is 386? It's in that range. So it gives you violet. So you need at least violet light in order to move that. In recent years, the depletion of the ozone layer has been a topic of much research. Will this depletion have a positive or negative effect on the functioning of solar panels? Explain your answer. The depletion of the ozone layer is a terrible thing, but in terms of solar panels, it's a fabulous thing. Okay? I took the people who said negative, it might give too much sunlight. I gave you some of your marks, but really, what do you got? You've got more UV light, more intense. So it's more intense UV coming through. Therefore, more electrons released, and therefore more current. And that just means you've got more electricity. So that all needs to come through in the photoelectric effect. we've got this diagram. We're given lots of information about it. Interestingly, this diagram shows me that I can move and rotate the solar panel around, and I can also change the angle that the solar panel has with the sun. And what's going to happen is I'm going to move a motor over here. I'm going to have a powerful jet stream over there, and I am going to notice how high that ball goes. But they don't necessarily say that exactly. Solar panel is rotated, and its inclination can be adjusted. When exposed, the solar panel generates electrical energy. The water pump emits a jet of water, and the strength of the current determines the power output of the pump, which in turn determines the strength of the jet of water, which in turn determines the height of the ball. So, from your knowledge, what characteristic of light affects the strength of current that is produced? And that is the intensity of the light. Gives you a stronger or weaker current. Doesn't have the kinetic energy of those electrons is because of the frequency of the light. How can the characteristic mentioned in 4.1 be adjusted for the apparatus? So how do I get more intense light? Well, I can. It's 2 marks. I can firstly rotate panel to face sun. And then I can adjust the angle of panel to optimum inclination. Which, by the way, has to do with the latitude on the Earth and stuff like that. It does change a bit depending on where you are on the planet. In Johannesburg, I think we need our angle to be about 23 degrees, but that's not going to be tested. Okay, the apparatus above is used to investigate the factors that affect the amount of current produced in the circuit. Name 2 other measurable quantities that could be used as dependent variables in the investigation. So we could either look at the ammeter, which is what they say you're going to do. So you can't use that again. You can't tell me you're going to work out how much current there is or what is the ammeter, but you can see height of the ball. Sorry. And you can see strength of jet. Finally, both sodium, this was badly answered, please listen carefully. Both sodium and neon are used in lighted signs in street lamps. The diagram below shows the atomic emission spectra for the two. Explain why sodium and neon have different emission spectra from one another. So, the whole point of these is that they are fingerprints for each element. And that is because each element has got a different arrangement of electrons, a different number of electrons, and different gaps in their energy levels. So these electrons would emit different amounts of energy and therefore different frequencies of light at different points on their emission spectrum. How would a sodium lamp appear different from a neon lamp? I gave you a color picture here. Surely color's got something to do with it. So sodium seems to be a yellow lamp, whilst neon will be an orange-red lamp. That was what I expected to see.